I'm Max Schweger. I'm one of the co-organizers of this workshop. I'm not able to be there at ICRA in person, unfortunately. I would love to, but I'm super happy that many people are there in person. So I am very pleased to introduce our next speaker, Ransalu Senananyake, who has been a postdoc at Stanford for a little while, and I believe is probably on the job market very soon for professorships, if not currently. So definitely keep a lookout for his job talks and applications and so on. He's an expert in Bayesian representation of dynamic maps. So oftentimes for representing scenes for autonomous driving, and has also done quite a bit of work recently in driver modeling and driver interactions in autonomous driving. But I think what really distinguishes his work as a focus on a Bayesian or an uncertainty quantifying perspective. And so Ransalu, please take it away.
Yeah, thank you very much for the kind introduction, Mac. Let me share my screen first. Okay. Can you all see my screen? Okay, perfect. Okay.
Yep.
Yeah, so in today's workshop, we had all good discussion about implicit representations, and I'm going to supplement with this uncertainty perspective of implicit representations. Okay, let's start with a video. So what is the reason for this crash? Maybe the vehicles did not see each other because it's too dark, or it could be partially occluded. Maybe one vehicle tried to brake, but because of snow, it was slippery. So when we try to deploy robots in this kind of real world environment, there's so much uncertainty. So this uncertainty can arise from various sources. It could be due to hardware limitations, model limitations, which means maybe some very simple models. Partial observability, which includes occlusions. So some of these are internal sources, and there are also external sources. For instance, if there are moving vehicles around, maybe pedestrians, human, we really do not know what they are doing or what their objective functions are. So there's some uncertainty around that as well. Also, if we try to deploy a robot in a totally different environment that it has never seen, then that could also result in uncertainty. So this is not an exhaustive list. I just wanted to identify there are various sources. So in my work, I basically get data from various sensors, camera, LiDAR, and radar. And in today's talk, I will mostly focus on LiDAR and radar, basically, where we have some depth information. So we get this data and we create a representation of the world. Then use that representation for decision making. So I'm not only interested in just the representation, but I'm also interested in the uncertainty at the intersection of perception and decision making. Because when we have the uncertainty, the robot can look at various possible options and then make the best decision. When I say the best is always like a trade-off between safety, efficiency, and so many other factors. Okay, when I say uncertainty, there are two types of uncertainty: aleatoric uncertainty and the epistemic uncertainty, or in simple terms, known unknowns and unknown unknowns. In most robotics problems, we mostly consider this aleatoric uncertainty. So to show it more pictorially, say if we want to estimate the distance to a nearby vehicle, we can never get the exact distance. There's some noise. So this error margin is basically the aleatoric uncertainty. We can't really reduce it. Whereas epistemic uncertainty is totally different. It's about the uncertainty about things that we do not know. For instance, so whatever in front of this red car is totally occluded and we really do not know what is in front. It could even be like a truck. So in areas where we do not have data, we cannot see, is basically the epistemic uncertainty. We show it in a plot. These like little error bars around data is the aleatory uncertainty. In areas where we do not have data, this uncertainty is the epistemic uncertainty. So estimating epistemic uncertainty is hard. It's okay not to know something, but we should at least know that we do not know. That is why estimating the epistemic uncertainty is important. So we can get data from different sensors, and I said like we need a representation with uncertainty. But what is the real representation we need? In robotics, we need the map. Especially in field robotics, we really need a map of the environment. Or in same way for manipulation, maybe a surface. Right? But for real robotic application, not just the surface, but a surface that changes in both space and time. So we need a spatial-temporal representation. So this representation, one of the simplest things we need is the occupancy of the environment. Which areas are occupied, which areas are free. If we know which areas are free, then the robot can move or navigate in that area. But for dynamic environment, just occupancy is not sufficient. We need to look at direction, speed, acceleration, semantics, in addition to occupancy. And there are so many other quantities. So in my work, I try to develop maps which represent all these dynamic quantities and importantly, their associated uncertainty, so that we can do all like safe and robust decision making. Let me show you an example what I mean by estimating or quantifying epistemic uncertainty. So this is a Mars rover. And on Mars, you have boulders like this. In this case, the quantity of interest is the elevation. We need to build an elevation map like this. For that, we try to learn a function F. So this is implicit representation, and X is basically location. For given location, if we query this function, it will provide the mean elevation. We are not just interested in mean elevation, we are also interested in the uncertainty or the variance. Why? Because if we look closely, what is behind this boulder, it's a huge pit. The robot cannot actually see this view, but there's a huge pit. So that pit is shown here. We do not really see that area, therefore the variance is very high. If we do not consider this uncertainty, what would happen is the robot would go and fall in this pit, which would cost billions of dollars if this was on Mars. Right. Now that is an example of uncertainty, epistemic uncertainty. Now, when we try to learn this specific function F, we really need to care about what we are really going to do. For instance, like if it is in computer graphics, what we are really interested in, the most beautiful image or rendering. But in robotics, as Anju also highlighted, our objectives are slightly different. Because we have this like complex interaction between perception and decision making. We build a perception model for decision making, not the other way around. So special patterns are nonlinear. So we can have a function F, which can be a neural network, and our data is sparse, especially if you are using LiDAR or radar. Radar data is very sparse. Like we have few data points here and there. And if you want to build a representation, we have very few data points. When I say very few, it's compared to like a classification task. Say we have classification tasks to classify cats, dogs, trees, and so on. Compared to that kind of a task, we have very few data points for a given environment or a given object. So this is basically a small data problem in that sense. But this should also scale to really large environments. Say if you want to build a map of a city, so this technique should scale. And I already highlighted the importance of uncertainty in robotics, but just because we want uncertainty, it's hard to use a technique like Gaussian processors in practice, because even we use the fastest version like data Gaussian processors, they are not fast enough. Right? That's why we really need to think about how to develop a function F that can actually tackle some of these challenges and have the necessary properties. For that, let me introduce Bayesian Hilbert mapping framework. for the simplicity, I consider this kind of a circular building. We have a circular building and a robot at the middle, and it has a LiDAR, which can measure the distance to nearby walls. So I sample some data points in between the robot and the LiDAR points. And so that from that, we can create a data set. So we have laser hits and free points. And our objective is to create this kind of a circular boundary. So if we use a simple linear model, we cannot really get this kind of a circular boundary. What we can do is we can project our data into high dimensional space. In this simple example, 2D to 3D. In that space, we have linear separation. Once we do that separation, we can come back to our original space. Once we have this like kind of a functional mapping, we can query at any resolution and we can create this kind of a surface. It's not a surface actually, in this case, it's like a map. Okay, but in the real world, we do not have circular buildings. This is what we encounter in the real world. Therefore, we do not project 2D to 3D, but instead we introduce some pseudo points called hinge points. Just I introduce them randomly in the environment. Then I measure the distance between my pseudo points and original points using a similarity function. So these kernels are similarity functions. They take two inputs. And if the inputs are similar, then the value is high. If they are dissimilar, then the value is low. One of the simplest ways to compute this distance is a squared exponential kernel. But I have to make a couple of remarks here. We can use whatever the kernel or the similarity function we want. That is one thing. The other thing is, this is pretty much the same as an activation function. I will show you in a couple of minutes. So the choice is up to you. Okay, now we compute the distance for each and every point. So we have a feature vector. So this is like a high dimensional projection. This is actually what happens in a neural network exactly. So if we consider the first layer is like a linear representation, right? And then we transform. So it's like if it is just single layer, this is just linear regression. Then the second layer, it's again linear regression, but with some transformed values. So this is what we keep doing. And the important thing here is this activation function. So what should we choose for this activation function? Now, this is, in this axis, I show the complexity of activation functions. If it is linear, it would underfit. But if it is something like slightly, it's almost linear, but slightly nonlinear. For instance, something like ReLU or TANH, they have really good generalization performance, and therefore they are good for classification tasks like classifying dogs, parrots, trees, cats, and so on. Then we have a large data set. But for implicit representations, what we are actually doing is, we are not generalizing. What we are trying to do is we almost try to overfit, right? Because for a given point cloud, what we want is to build a network that corresponds to the point cloud. So we try to almost overfit. For overfitting, more complex activation functions are more useful, something like Gaussians or sinusoidal. This is also called periodics. So which one is better actually out of these two? So I recommend like looking at this paper from Ramos. Basically, if this is the shape we want to look at, so this is basically a building, like a 2D projection of a building. So we can see this blue area is the area that we need to navigate. This is the blue area you can see if you use Gaussian activations. If you use sinusoidal or like same as periodic activations, this is what you get. You still get blue area, but the problem with these sinusoidal activations is you cannot extrapolate or interpolate. For instance, so if we are moving a robot around a building, we are not just interested in where the surface is. We need to really know what's in between surfaces, because that's where the robot's going to move, right? So that kind of a task, Gaussian activation functions are really good. Whereas sinusoidal activation functions, by definition, they overfit. So these are just two activation functions, or in other words, they are just kernels, whatever the language we speak. Another good thing about this Gaussian activation function is they are more interpretable because it has a shape and we know like they are spatially, how much they are spatially related. So this is our neural network. I represent again in a slightly different form. So what happens in a neural network, in the first few layers, they try to extract features. Right? That's why so in Networ and other representations, you have like periodic or positional encoding at the beginning. And towards later layers, it tries to classify. Right? So this is like a more simplistic representation just to highlight the concept. For this automatic feature extraction, you can use these sinusoidals or cosines. That's one way. You could use periodic, you could use Gaussians. There are so many different ways. These are Newstrom features. There can be 1,000 different ways. So what I want to highlight is like the first layer. In the first layer, we try to extract features. First few layers. Right. So these sinusoidals, so it depends on, like in machine learning, you call these Fourier features, random Fourier features. It's from actually Rahimi and Ben Recht. So in field robotics, you call it Fourier features. In NLP, in computer vision, you call it positional encoding. It's just a different wording. How you get all these sinusoidal is just from Fourier transform. We have our original function. We just apply the Fourier transform. We have this complex number I. Because of this e to the power complex number I, we can decompose it as cosines and sines. That's how we got to all these like cosines and sine. And this is how they become activation functions. Okay, now for geometric processing, what do we really need? Do we need to go deeper or go wider? In any machine learning problem, there are three things, right? So we have data. In our case, data is almost fixed. Then we have our model and we have our inference algorithm. If you use a neural network, 99.9% of the case, it's backpropagation. It's just the simplest inference algorithm. Okay, for the model, either we can have really good features here and a simple classifier. Or option 2 is we can just get some features somehow, use whatever the activation function, and then have a really complex classifier. So I would choose option number 1 because there are a couple of reasons. Number 1 is if we have good features, then we need only a very simple classifier. Even this could be like a single layer neural network. Or it could be like we don't need a neural network at all, as Anju showed earlier. Right? So if you have a very simple classifier, which means our model is small models are always good for robots. Few parameters means the runtime is much faster and easy to store in a robot. And the other advantage for me is it's much easier to estimate the epistemic uncertainty when we have a simpler classifier. Okay, let's come to inference. So in this case, I just consider, in this case, just a linear model, and I have this non-linearity because I'm looking at occupancy. Occupancy is binary, occupied or not. That is why I have sigma. To get the epistemic uncertainty, I introduce probability distributions or the weights. So in this case, if you think about a neural networks, you just need probability distributions or the weights of the neural network. Right? Now in this case, it's simple. We have a Bernoulli likelihood. Then we have Bernoulli likelihood, some Gaussian prior, but posterior becomes intractable because of the Bernoulli likelihood, and we have to resort to some approximation algorithms. So we can do that using variational inference for faster results, or much for better results, you could do MCMC or your favorite inference algorithm. Right. Now, okay, so if you introduce probability distributions or weights, we can get uncertainty. But as I mentioned, we also need to develop the best possible activation function for the kernel. Therefore, I introduce probability distributions over these parameters of the activation function as well. Basically, we learn the activation function or the kernel. I'm not going to go through all like how to do that, but say we do some inference and get our all the parameters. So this is a data set. In this area, we do not have data. This is red, like LiDAR hits. This is blue, which basically free area. And this is the map we get. In green means in that area, we do not have data. So what I want to highlight is, so when we have these like Gaussian shaped kernels or activation functions, they actually align with the obstacle. You can see they align with the obstacle over when we optimize it over several iterations. We can also look at the weights, right? So one other result is if we look at the feature count, this is like more like the width of the network, right? To get the same accuracy, say 90% accuracy, we only need a fewer number of kernels. So like a width can be much smaller if we learn the kernels or learn the activation function. So we really need to think about like having a really good set of activation functions for the best possible representation. So right, so now we can scale this. So this is like a car in a simulated environment. We can get the mean occupancy, and the variance of the occupancy is so behind buildings. This has a LiDAR. The LiDAR cannot see what is behind the building. That is why the variance or the uncertainty is really high in some areas. We can keep doing this and build this kind of maps for really large environments. This is occupancy. You could do this for surfaces. What you need to do is like you need to change the likelihood I showed you. So this is like the mean, and this is the variance. So if we say, okay, give me the 95% confident surface, it is possible to extract. Okay. Now we could do this the same for velocity. So velocity is now not a single quantity, but it's also a distribution like this. So this is some radar data. We can get radar data and we can estimate velocities, and we can do the same thing from accelerometer data for UAVs and build this kind of, say, 95% or whatever the probability you want, say 50% confident, like safe view. Now, with this kind of a representation, we don't need to really learn from scratch. One thing that we did was like, because what we have here is basic geometries, right? In the environment, we don't have so many shapes. So we can initially learn this set of like a geometric primitives, and then we encounter a new environment. We can look at the correspondence between geometries and just transfer the parameters from one environment to the other environment. And we can keep doing this and build this kind of maps. Right, so I'm going to just show you some other things we can do with this kind of an implicit representation. Say if you have multiple robots operating in, like, say, 4 corners of a building, we can let them learn 4 different maps, and finally combine to have a single implicit representation. So this would be like a single model. We can also look at multimodality using mixed density network. Also the associated uncertainty. So this is like more like a directional map. If we want to look at spatial temporal features, we can, because of the modularity, we can combine LSTMs and with these like kind of kernel features. Then one other cool thing that we can do is we can try to predict into the future, like what would be the implicit surface in the next few seconds. What you see here are some cars, and these are some pedestrians. You could look at like Gusilini's webpage if you want more details about this. Okay. So because in robotics, sometimes we need to predict ahead to make a more meaningful decision. By the way, this is some very old work. That's why like some of the rendering is not really good. And so I work on mostly on like modeling and say uncertainty. So again, like some others like Vita has worked on this like mapping really large environments. using this kind of representations. These are some of the results. By the way, colors here are not like nerf because these are just superimposed on the constructed image. So we don't need to confuse this. So these are purely from LiDAR pointers, not from images. Okay, so just to summarize, so I just presented this Bayesian Hilbert mapping framework to model implicit surfaces or environments, and more importantly, their associated uncertainties. For an efficient implicit representation, what we really need is a simple model. If you have a simple model, it's much easier to get the uncertainty. So to get a simple model, we really need to work on getting a good model, especially getting good features. To get good features, we really need to work on like having a really nice set of activation functions and learning all these more meaningful activation functions rather than just picking something randomly. So you can find most of this code online on my GitHub. And to conclude, right, so in robotics, we have this like perception, decision-making, all the interaction. So what we just need is not accuracy or building the nicest, beautiful model, but we really need to look at other aspects such as uncertainty, although getting those quantities is kind of challenging. With that, I'd like to thank all my collaborators, students, advisors who has been working with me. And if you have any questions, you can just drop me an email later, or you can find most of the stuff on my website.
Great.
Any questions?
Great, thanks. Let's give Ransalu a hand. All right, so let's go ahead and open it up for questions for Ransalu, and then we're going to have a panel with the last three speakers. I hope Angju and Shuran, you're both around and you're free to hang around for another half an hour to just have a conversation. Excellent. All right, so first, any questions for Ransalu? And I'm sorry, I can't see the audience, so I'm going to have to ask for Preston. Can you help me out?
Yeah, we got it, Mac. Yeah, we got
Excellent.
it.
I'll start with a question if we don't have any to open with. So Ransalu, I really appreciate your focus on uncertainty. That is so important in robotics and when you're involving action and planning. I'm curious about in your framework, kind of scalability and what happens as the number of hinge points grows, or how do you manage the number of hinge points, or as the data keeps growing, as the robot keeps moving around and collecting the data? How do you manage that complexity?
Right. So yeah, so that's something we can handle with this kind of like domain adaptation. So we can keep increasing the number of hinge points. It's like still it's like, say, if we come up with like a really big network, so how can we really handle really large environments, right? We need to keep increasing the number of parameters and relearn everything. So similarly, here we have to increase the number of hinge points as the robot moves. I guess we can try to do domain transfer like this. Those are the two main solutions.